Hi, good morning. Today we are going to learn about Chapter 6, Chemical Equilibrium. We have three subtopics under chemical equilibrium: 6.1 Dynamic Equilibrium, 6.2 Equilibrium Constant, 6.3 Le Chatelier's Principle. Now we start with 6.1 Dynamic Equilibrium. These are the following learning outcomes that we will cover under this chapter. Okay, to start with, we look at reversible and non-reversible equation. Non-reversible, the reaction that proceed in only one direction, that is toward the formation of product. For example, A plus B produces C plus D. The irreversible arrow indicates non-reversible reaction. A and B reacts to form C and D, forward reaction. However, C and D does not react to form A and B. This is a non-reversible reaction. For example, magnesium react with hydrochloric acid aqueous, produces magnesium chloride and releases hydrogen gas. This is non-reversible reaction. For reversible reaction, this is the arrow that we normally use in the equation. A plus B in equilibrium with C plus D. Consider the above reversible reaction which occurs in both forward and reverse directions. When molecules of A and B, excuse me, when molecules of reactant A and B react, molecules of product C and D are formed. As soon as some product molecules, that is C and D, are formed, the reverse process begins to take place, in which reactants A and B are formed from the products. So this is reversible reaction. The reversible arrow indicates the reversible reaction. Forward reaction, reaction proceeds from left to right, that is formation of C and D. And for the reverse reaction, reaction proceeds from right to left, formation of A and B. The net concentration of A, B, C, and D do not change. Some examples of reversible reactions are the Haber process. Nitrogen gas react with hydrogen gas to produce ammonia in equilibrium. Decomposition of PCl5 in equilibrium with PCl3 and Cl2. Stage 2 in contact process, sulfur dioxide react with oxygen in equilibrium with sulfur trioxide. State of equilibrium. Equilibrium is a state in which there are no observable changes as time goes by. Chemical equilibrium. Under chemical equilibrium, chemical composition of system does not change at dynamic equilibrium. For example, N2O4 in equilibrium with 2NO2. For the above system, at equilibrium state, the concentration of the reactants N2O4 and products NO2 remain constant over the time, and there is no visible changes in the system. This is referring to chemical equilibrium. At dynamic equilibrium, whereas physical equilibrium, a system whose physical state does not change when a dynamic equilibrium is reached. You can check here. Both water liquid and water vapor exist at dynamic equilibrium. There is no physical changes. So this is called physical equilibrium. Now, characteristics of a system in equilibrium. This is very important. A system in chemical equilibrium has the following characteristic. Of course, we are focusing on chemical equilibrium rather than physical equilibrium. So a system in chemical equilibrium has the following characteristic. Occurs only in a closed system. Forward and reverse reaction proceed at equal rates. The reaction quotient Q is equal to equilibrium constant K. The properties such as concentrations, pressure, and color of the reactants and products are constant over time. The point at which the rate of forward reaction equals to rate of the reverse reaction, the system said to be at dynamic equilibrium. Now we consider this reaction, this reversible reaction, A plus P in equilibrium with C plus D. Students can see the graph plotted here or sketched here is concentration versus time. A and B is the reactant. As time goes by, A and B decreases, while the product C and D, as time goes by, increases. Okay, now we try to understand the graph here or the diagram here. As the reaction progresses, C and D increases with time. Yes, they are product, while A and B decreases with time because they are reactant. At time Ta, there is no net change in the concentration of products or reactants. System state to be in the equilibrium state. Okay, you can see in the diagram Ta, beyond Ta, the concentration of both products and reactants become constant. There is no changes in the concentration. Now, beyond that point, beginning from that point and beyond that point, system said to be in dynamic equilibrium because the reaction does not stop. Sorry, the reaction did not stop because the concentration is still there for A and B. It's just it become constant. Whereas before point Ta, concentration of product will increase, concentration of reactant will decrease. So beyond point Ta, both concentration become constant. So concentration become constant, however, reaction did not stop. At this point, we also can conclude the rate of forward reaction, that is A plus B produces C plus D, equals to rate of reverse reaction, that is C plus D produces A plus B. Figure 2 shows the rate changes of both forward and reverse reaction over time. The first graph just now we discussed is a concentration versus time. Now is a rate versus time. And students can see rate of forward reaction decreases, rate of reverse reaction increases. And beyond point Ta, at certain time, the forward reaction will be equal to the reverse reaction. So system said to be at dynamic equilibrium. Excuse me. The rate of forward reaction decreases in time because the amount of reactant decreases, while the rate of reverse reaction increases since the concentration of product increase. At first, the rate of reverse reaction is zero because no product formed. So student can see reverse reaction start at when time equals zero, the rate is zero, shows that there is no product initially. Okay, but as the reaction progress, the product is being formed, so the concentration of the product will slowly increase. As the reaction proceeds, C and D increases with time, hence the rate of reaction also increases. For example, let's look at this one, N2O4 in equilibrium with 2NO2. The rate of forward reaction N2O4 produces NO2, while the rate of reverse reaction NO2 produces N2O4. Now, when both rate is equal, as you see in the diagram, the conclusion is the concentration of N2O4 and NO2 remain constant. However, the value is not same. They only remain constant when the system is at equilibrium. Okay, next important thing about 6.1 is a law of chemical equilibrium. The equilibrium concentration of reactants and products are related by law of mass action or law of chemical equilibrium, which defined as the rate at which a chemical reaction takes place at a given temperature is proportional to the product of active masses of the reactants. When a reversible reaction has achieved dynamic equilibrium at constant temperature, the ratio of reactant to product concentration has a constant value K. So let's say we have A plus B produces C plus D, or in equilibrium with C plus D. We can write the equilibrium constant K as follow. That is C to power C, D to power D, divided by A to power A, B to power B. This is the expression for equilibrium constant. So concentration is given in the unit molar. Please take note, the small case ABCD refers to stoichiometric coefficient for the reacting species ABCD in the Barrett's equation. Note, magnitude of K indicates how far the reaction proceeds toward product at a given temperature. For a reverse reaction, the other way, C plus D produces A plus B. For the reverse reaction, we can also write the equilibrium constant K. A to power A, B to power B, divided by C to power C, D to power D. Okay. But let's say for this reaction, C plus D produces A plus B. We want to find the reverse reaction. Then we have to use the term K prime. K prime equals to 1 over K.